Hello everyone, my name is Andrej, and today we're going to be talking about invalid opcode and what can we learn from it to understand the EVM a little bit better. So usually when you develop your contracts and they fail, most likely you've come up to something like this, just invalid opcode, an indication that the contract failed and you don't know where really to start looking. So wouldn't it be better to go from something like this to something more detailed, something you can see in other languages. So full stack trace of where your transaction went to when it failed and the exact line of Solidity source code where it failed, so you can easily fix it. In this session, we're going to try just that. We're going to split it into two parts. The first part being going from the position in bytecode where the transaction failed, which we can get from the EVM, to the exact line of Solidity source code, which we can then use to debug. And the second part is build on top of it and get even more information by getting the whole call stack of the failure. So let's start. The first part is source mapping. And what source mapping really is in the first place? Well, it's a method of going from a low-level bytecode location which is not easily debuggable, to something that is a Solidity source code line. So how would that process look like in the overview? So we would take the bytecode and we would transform it into something more readable. So we would transform it into instructions. And from there, we would find the source mapping for the instruction that we found and use that source mapping to get to the final Solidity source code. That's the overall process. But how do we do it exactly? Let's get started. We start with bytecode. And we know that bytecode is just a sequence of instructions that is generated by the Solidity compiler and used to be deployed on the Ethereum network to be executed. And when the transaction fails, we can get from the EVM the exact line, position in the bytecode, marked here in red, where the failure happened. So if we wanted to know which instruction caused the failure, because bytecode is pretty unreadable, we would first have to transform the bytecode into instructions. That process of transforming bytecode into instruction is called disassembling. There are a couple of tools online which you can use to disassemble Solidity or EVM bytecode into a set of instructions, but here we're going to do it manually. We're going to start by splitting the bytecode into a sequence of bytes, and we're going to mark the index of each byte in the bytecode to the left in green. If we wanted to convert this sequence of bytes into a sequence of instructions, what we would want to do ideally is group sequences of one or more bytes into groups which form instructions. And how would we do it? We know that each instruction starts with an opcode. An opcode is a unique value that identifies each instruction, and with this mapping, we know if we need to take any additional bytes to form the entire instruction. So we can use the bytecode and the mapping of opcodes to instructions to go to the right here and see how we can sort of make out which instruction starts at which position in bytecode. We then want to group all the bytes that belong to a single instruction and kind of make out the final form here. The thing you'll notice here is we have a second index on the right, which is essentially a position of the instruction in the instruction sequence. So the difference between the two, the left and the right, is because the left one is the position in the bytecode, and the right one is the index of the instruction. And those two aren't the same because one instruction can have one or more bytes that's created for it. So the final form is we have a sequence of instructions that we derived from the bytecode and 2 indexes which we use to look up the instructions in various ways. To the left we have the bytecode index, and the right we have the instruction number. So as an example to what we can do with this information, if we have the bytecode and the transaction failed, we get the location where the transaction failed, and we get the exact instruction which caused the failure. But we still have that index on the right. Why do we need that index in the first place? Well, it turns out that when Solidity generates EVM instructions from source code, it doesn't really care about the positions in bytecodes for each instruction. It just cares about which instruction was generated by which line in Solidity. It leaves the bytecode stuff to the EVM. So as an additional output of the Solidity compiler, what we get aside from the bytecode is a source map. So a source map is a special format of a file which Solidity uses to to specify which instruction belongs to which line in source code. So we can see that this format here is not that clear what it does. So let's get into it a bit better. So what we know that we get 1 line for 1 instruction of 1 EVM instruction. We can see that we can shorten each mapping by 1 or more fields if that field is the same as the previous one. And in case where 1 line generates more instructions, so the same line generates, for example, 5 instructions, we can omit the entire mapping, and we know that it is the same for the set of instructions. So what is contained in each source mapping? Well, we know where the line that generated the EVM was located. So an offset in the file. That's a mistake. That's an example. Okay. Yeah. So the offset of the line in source code. We know the length of the line that generated it, and the index of the file which generated the instruction. And the 4th indicator is the jump indicator, and we'll get to it in a while. So as an example, how you would read a mapping like this is you would first take the file index and get to the file that generated instruction. You would then find the offset where the line starts, and finally you're going to get the length of the line and get to the final source code that generated instruction. So we made it. We now have all the information we basically need to recreate the line in Solidity which failed the transaction. Let's see it in an example. So we start with bytecode, and we see that the transaction fails somewhere. And we use that position in bytecode, which is the only information we have, to get to the instruction that caused the failure. We now use the index to the right to find the source mapping for the instruction, because as we talked earlier, instructions and source mappings are one-to-one. So index for an instruction is the same for the source mapping. And finally, we know how to take the source mapping and read it and get to the final source code which caused the failure. So that's the final step of our first part, and we effectively already have a lot of information we can use to debug our contracts. But what about if we wanted to give even more information to the developer to quickly find even more obscure bugs? So why exactly would we use a call stack in the first place? Well, imagine you have a payment processing contract, and you have a single dedicated method that does the transfers from one account to the other. And you use that method in a lot of places. And if, for any reason, a transaction fails in that part of the code, you don't really know from where the failure came from. So you maybe have 10 calls to the method, and for some reason it fails. You don't really know where to start looking, and you would like more visibility. So as an example here, let's say you have a method that failed. What you would want to get is the caller of it and go all the way up to the initial transaction. So you have the whole path, and you know exactly which route your program took when it failed. So ideally, if we had something like this to start with, what we would want is get all the other locations of function calls where the transaction failed. But we can't have that easily. We can use an EVM Tracer. An EVM Tracer plugs directly into the EVM and listens for calls like jumps, calls, and returns in order to build a virtual stack and keep track of it during the execution of the contract. And in case of failure, return it to the user at the point of failure. But that is pretty involved, and we're not going to deal with it right now. What we're going to be doing is using a shortcut. We have a couple of tools at our disposal that can shorten our journey quite a bit. So the first one is, how do we know where the program went as it executed? Well, we can call a function here on the node, on the RPC API of the node, and get the JSON representation of the whole execution of the transaction. So that means we know which instruction generated and in which order until the failure. So if we have the PC here represents the position in the bytecode. If we wanted to enhance this information, we already know how to get the source mappings from the bytecode positions. So we would do just that. But what do we know with this that we didn't know with the bytecode? Well, remember the fourth element of the source mapping, and that's the jump indicator. We can use it to recreate the stack after the execution to get the same result essentially. So we would go and run through each of the lines we got from the endpoint, and if we see an I, that means the instruction went into a function, and we would add it to a call stack. If we see a dash, that means no changes have been made, and we can just discard it. And if we see an O, that means the instruction went out of the function, and we can remove it because if we go into something and then leave it, it doesn't really affect our path of failure, so we can skip it. And then go through the rest of the instructions, adding and removing entries until we get to the final failing instruction, add it to the call stack, and that's what we need. So if we want to see a more detailed example of this, we see that we go into a function. That function does some work. It's not important what work it does, and it returns. So we can discard the elements that were associated with that function because we don't really care about it. We care about only the functions that go inside and then fail. And we go through the rest, like enter another function here, from which we leave right away. So we discard the one we called that didn't actually fail. And once we enter the final one, let's say we fail here. So this is the stack we would get by using the pushing and popping method. So what do these source mappings represent? Well, if we went and used the method of converting the source map to a position in source code, we would see that each line is essentially the entry point into a function which finally caused the failure. So this should be our stack trace. And if we convert it into a more readable format, we get something like this. So that's how you go to the complete stack trace and have a way easier time debugging your contracts. Thank you. My name was Andrej, and I come from Tenderly. We do just this. Do we have any questions?
Can anyone hear me?
So your talk presented this wonderful project as if it was entirely and exclusively aimed at developers. However, with smart contracts, I believe that looking at what happened during execution in the source code is interesting not only for developers, but actually to users as well. Because if I submit a transaction and something happens that I did not expect, which is not even necessarily an invalid opcode, so it's not even necessarily a failure, it's just that I didn't get the money or something else happened that when I expected. As a user, I would like to see what happened, like step by step. So are the tools that you're building suitable, not right now, but in the future, suitable for that kind of use case?
Yeah, so if the question is this the developer-only tool? Well, no. At Tenderly, we use this method. I mean, this method is like full developer-only. What you need is what you get to get the things you need. But at Tenderly, we are building all the human-readable stuff on top of it. So we take this knowledge and convert it into something more readable. So definitely you can do that. I mean, you can use the low-level information here to get more things than just when something failed, you know. Anyone else? Okay.
Where do you get the artifacts from? So as far as I understand, you're writing the command line tool, and it's a proxy, and you connect truffle to that. So as far as I know, truffle artifacts don't have exactly enough information to do that, because source maps map back to file indices, and file indices, you need the list of files, which truffle artifacts don't have. So you kind of need to recompile all the contracts.
Well, we use just the truffle build artifacts because I believe in the truffle configuration you only have one file, so it's concatenated. The source should be at least concatenated for each contract that you deploy. The artifact for that contract contains the source maps and everything you need. So you just use that source with that source map, and it should have everything you need. We don't need to recompile anything. So.
And the proxy just reads the artifact.
Well, the proxy, yeah, you get the proxy is a tool which you can put in front of your node. So you're doing local development in case of anybody else doesn't know. You do local development, you put Tenderly proxy in front of it, and each time your transaction fails, for example, in truffle test, instead of invalid opcode, you would get something like the last slide here we got. So what we do is listen to all connections as if we are a node. For everything we're not interested in, we just pass to the node directly and return it back. And we check if the transaction failed in case of send transaction, and do our work from there.
Do you support call failures?
No, I believe call failures not at the moment, but it can be retrofitted inside.
This is only for Solidity, though, right?
Yeah, this is the question was: is this only for Solidity? Yes.
And then you have an API that we can call to get the stack trace back automatically. You have tools that we can use.
Yeah. So what you can use right now is the CLI tool, but if that's more involved than you would potentially like, we are building a dashboard which you can add your contracts there, and we can automatically list out all the failures that you had on the contract. And when we released it for the conference, so you can check it out. Anyone else? I think that's it then.